Hello everybody, my name is Clemens Lachner and today I want to talk about a privacy-preserving system for AI-assisted video analytics. First of all, let me briefly introduce you to the area of research regarding our proposed system and its context. The system is designed to operate in the edge computing area. This area comprises a very heterogeneous hardware environment in terms of computational, network and storage capabilities. The system we propose is not necessarily designed for any specific type of hardware. However, we conducted our experiments on resource-constrained devices, which are small in size, typically found in smart city scenarios like smart lampposts and so on. The main purpose of the system is to perform all kinds of video analytics at the edge. In a smart city scenario, potential use case could be traffic monitoring, public surveillance, object detection or tracking, and so forth. However, as you can imagine, many of such use cases also need to implement non-functional requirements such as privacy and security. Our system design focuses on data protection, which per definition deals with the protection of personal data, but the system is not limited to data protection only. So, now that you know the context of our proposed system, let me explain the problem our system aims to solve, or the generic threats it tries to mitigate, which video analytics are exposed to. Obviously, depending on where you live in a modern city, you will notice the widespread deployment of video cameras. Regardless of the purpose they serve, that is, surveillance or analytics, or the role they play in specific applications, most of the time such systems raise several security and privacy concerns. Typically, such systems need to adhere to at least some kind of privacy and security policies. For example, such policies could describe the appropriate handling and implementation of data protection. A prominent example of such policies is the EU's General Data Protection Regulation, short GDPR, which regulates the protection of natural persons with regard to the processing of personal data and the free movement of such data. Video analytics on the edge are often heavily supported by artificial intelligence also. As you can see in the left-hand picture, a modern AI is capable of inferring a lot of valuable but also personally identifiable information from a video stream. Extracting personally identifiable information, however, is not limited to applications involving face detection or recognition, but also things like the automatic detection of license plates of vehicles and many more. So during the research for the paper, we found various different approaches that deal with adequate protection of such personally identifiable information. However, most of the proposed solutions focus on some form of encryption mechanisms and strategies. For instance, some identify so-called regions of interest in each frame of a video. Such a region could be the area spanning across a detected face in a video frame. And then only this particular area in the frame is encrypted or anonymized with dedicated denaturing effects like pixelating or blurring. The design and implementation of specialized access control mechanisms is another strategy that is heavily researched with regard to the stated problem. However, in our paper, we follow an orthogonal approach and ask the question, for many use case scenarios involving video analytics, is it really necessary to distribute the raw video feed at all? We argue that there are a lot of use cases where accessing and processing extracted features of interest from a video may be sufficient and, most of all, highly effective in protecting sensitive data. Modern AI frameworks and their well-trained models offer a great potential to extract all kinds of valuable information from video data. Hence, we came up with a straightforward system design that preserves privacy by extracting relevant features from video data with the help of modern AI, and only these features will be distributed in a secure manner, which I will be explaining in a minute. First of all, if you look at the picture on the slide, in the box labeled A is depicted the part of the system that does the video processing. This could be deployed on the edge as local as possible, for instance in a smart lamppost, where the camera is installed also. The extracted information, that is the features, is then labeled, specifically encrypted and sent to an information database as as depicted in the box labeled B. I will explain the encryption process in more detail on the next slide. Applications that need to access the extracted information are provided with a specific key that specifies which particular data they are allowed to access. This specification is derived from a policy, which in turn is defined by some governing party. Now I will explain why a labeling of the extracted feature is needed and what the specific encryption strategy is all about. Our system relies on the so-called key policy attribute-based encryption scheme. In this scheme, ciphertexts are associated with sets of descriptive attributes or labels, and users or application keys are associated with policies. It is important to notice that the encryptor exerts no control over who has access to the data they encrypt, except by their choice of descriptive attributes for the data. Rather, they must trust that the key issuer issues the appropriate keys to grant or deny access to the appropriate users or applications. Let me give you an easy, tangible example. If you recall the image from the problem statement slide, you can see that an AI-inferred feature, like the estimated age, gender, and current emotional status of the recorded person, can be analyzed and distributed. So, if you want to analyze, for instance, the gender distribution in a given video, you then encrypt the inferred genders and simply label them gender, resulting in a ciphertext with the attribute gender. Only applications or users that hold a key which allows them to decrypt ciphertext with this particular attribute can now access extracted gender data from the video. This encryption strategy also comes with the benefit of not needing a redeployment of an application if a policy changes, for instance. Only the keys need to be updated in the most simple cases. In our evaluation, we tested if the system is feasible for edge computing scenario with respect to its performance. For people that do AI research as well, this might not be a big surprise, but nevertheless, we want to emphasize that the limiting factor performance-wise in the system is not the key policy attribute-based encryption scheme, but to a great extent the inferencing task of the used AI framework. Typically, the processing time for encryption scales linearly with CPU speed, and particularly if resource-constrained devices are involved in the system, hardware acceleration like ECC support are really game-changing. Regarding encryption, our proposed system also significantly performs better than systems that encrypt, example given, whole video frames, simply due to the much more smaller plaintext size. However, we also have to notice that because AI inference needs a lot of computational resources, a decoupling or offloading of this task to more powerful devices may be advantageous. You have to pay attention though, if you consider offloading of AI inferring tasks, that this does not fail the whole purpose of the system, that is sending the raw video feed, for example, to the cloud. Considering data locality, a nearby more powerful edge node may also do the job, while the data must not necessarily leave the local premises. To conclude my presentation, I will quickly summarize the important details of our system. First of all, our system is designed for use cases where a transmission of raw video data is not needed. Therefore, maintaining maximum privacy, only relevant features are extracted from the video. Furthermore, the extracted information is only available for users or applications that are allowed to, which particular set of extracted information can be fine granularly defined via policies. The proposed key policy-based encryption scheme is not a limiting factor for edge computing systems, even if resource-constrained devices are involved. That's it from my side. I hope you enjoyed the presentation, and if you have comments, questions, observations, please do not hesitate to contact me via email. Thank you.